Hi friends, welcome back to our series of sessions on energy conservation and management. Today we shall be discussing about the most important parameter, that is the power factor, and the related electrical terminology. In the utilization of electrical energy, there are three fundamental parameters which one has to understand. They are load factor, diversity factor, and utilization factor. Normally, for low voltage consumers, only energy consumed is measured. But for a bulk electricity consumer with a high voltage connection, the meter used is called a trivector meter. This meter measures the maximum demand in kVA, energy consumed in kilowatt hours, and total apparent energy consumed in kVA-H. From these measurements, one can calculate the average power factor as kWh by kVA-H. Previously, these meters were electromagnetic, but with advancement in instrumentation and electronics, new meters have been developed. They are called TOD meters, time of the day meters. These meters not only record all the above mentioned quantities, but they also record the time these quantities were measured. Maximum demand is kVA-H measured during a prefixed time duration of either 15 minutes or 30 minutes, and then multiplied by either 4 or 2 respectively to give kVA-H per hour, that is kVA. Thus, at the end of each time cycle, the timer is reset and fresh measurement starts. Such measurements also ensures that an instantaneous load like starting of the motor does not affect the maximum demand measurement. Normally, a 15-minute timer is used for a contracted maximum demand exceeding 5 MVA, whereas a 30-minute timer is used for a contracted maximum demand less than 5 MVA. The provision was applicable, and the contracted demand is the demand mutually agreed between the supply company and the consumer by way of a signed contract. This demand forms the basis for working out of various capacities for the supply company and the consumer. Thus, the supply company makes arrangements to supply the required demand and expects the consumer to restrict his demand within that limit. If a consumer exceeds the demand, the supply company charges him a penalty. If the consumer draws less than 80% of the contracted maximum demand, the supply company charges him 80% of the CMD, called billing demand. Thus, the billing demand is higher of the two, 80% of the CMD or actual maximum demand established by the meter. This figure 80% may again vary from state to state, but the principle remains the same. Connected load is the sum of nameplate readings of all the equipment utilizing electricity inside the consumer installation. Normally, when the figure is worked out, standby equipment is not considered since only one of them is running at a time. Also, the figure is based on end utilizing equipment, and intermediate equipment like distribution transformers, motor control centers, etc. are not considered. Average load is energy consumption recorded divided by the operating hours of the plant. Load factor is equal to average load by maximum demand, which is always less than 1. Diversity factor is connected load divided by maximum demand, which is always more than 1. Utilization factor is equal to average load divided by connected load, which is always less than 1. Then utilization factor is the load factor divided by diversity factor. Utilization factor can easily be derived by multiplying both the numerator and denominator by maximum demand. That's about the connected load. It is important to note here that all the quantities must be worked out on the same unit basis of kilowatt or kVA. If maximum demand is measured in kVA, then using the power factor, it should be converted to kilowatt. Similarly, in a connected load, if the rating of any particular equipment is given in kVA, then using its rated power factor, it should be converted to kilowatt. From the above, it will amply clear that by reducing maximum demand, one can save a lot of money, and hence the control of maximum demand forms an essential part of energy conservation program. Similarly, achieving a load factor as close to unity as possible ensures that demand is uniform and energy is uniformly and well utilized. This also ensures that distribution losses are reduced. Then we have controlling the maximum demand. There are various methods of controlling the maximum demand. They can be shift non-essential loads to off-peak loads. For example, if one is working in a bottling plant, working in two shifts, then loads like the water treatment plant, the effluent treatment plant can be made during the third shift alone. Better coordination amongst departments. For example, in a cement plant where mines work only from sunrise to sunset, the colony water pumps, water treatment plants, etc., can be run only during sunset to sunrise. Next is improvement of the power factor gives a great relief to maximum demand. This is because for the given kilowatt, the unity power factor records the same kVA, but a 0.5 power factor records double the kVA. Since billing is done on the basis of kVA, a better power factor helps in controlling maximum demand. The above methods indicated are dependent on manual systems and hence are not reliable. The most modern method is to provide an automatic maximum demand controller, probably a microcontroller based instrument, which monitors the maximum demand by iterative projections and cuts off automatically non-essential loads as per priorities decided earlier. And the power factor, which is the most very important factor when it comes to electrical energy consumption. In case of pure resistive loads, the voltage, current, and resistance relations are linearly related. That is, V is equal to I into R and power kilowatt is equal to V into I. Active power is measured in kilowatt. Reactive power is measured in kVAR, kilovolt ampere reactive. The vector sum of the active power and the reactive power make up the total or apparent power used. This is the power generated by the state electricity boards for the user to perform a given amount of work. Total power is measured in kVA. The power factor is also a ratio of kilowatt to kVA, which is always less than equal to unity. This is represented by a famous triangular relation as shown in figure. We have the kilowatt in active power, then kVA total power, whereas PF is equal to kilowatt by kVA, that is the cos phi, and kVAR is the reactive power that we have on this side. The active power, which we normally call it as a shaft power required or true power required in kilowatt, and the reactive power required kVAR are 90 degrees apart vectorially in a pure inductive circuit. That is reactive power kVAR lagging the active kilowatt. The vector sum of the two is called the apparent power or kVA, as illustrated in the figure. And the kVA reflects the actual electrical load on distribution system. This can be compared with a beer analogy. Power factor is the percentage of apparent power that does real work. Understand power factor using a beer mug analogy. This is the kVAR, reactive power, which is wasted electricity, and kilowatt is the real power. And the sum of both kVAR and kilowatt, we are getting as kVA. That's exactly what we have. So power factor is equal to kilowatt divided by kilowatt square plus kVAR square, and which is nothing but we call it as a cos phi. So reactive power is a wasted electricity and usable electricity only the kilowatt. So that is what we usually understand the power factor. Then we also understand this is the resistive circuit where we have power factor is unity. We have voltage and current where we are on the same phase. Right? Then we have inductive current. You will see current inductive circuit lagging power factor because current always lags behind the voltage. Right? If the current leads behind the voltage, which happens in capacitive circuit, we normally call it as a leading power factor. Then for power factor correction, we have normally the example we are taking as a chemical industry which had installed a 1500 kVA transformer. The initial demand of the plant was 1160 kVA with power factor 0.7. The percentage loading of transformer was about 78%. because 1160 divided by 1500, we normally get it 77.3%. To improve the power factor and to avoid the penalty, the unit had added about 410 kVAR in the motor load end. This improved the power factor to 0.89 and reduced the required kVA to 913, which is the vector sum of kilowatt and kVAR. So if you see here, we have kVA 1160, kilowatt 812, and kVAR is 828. Now with the improved power factor, we have kW 812 and kVAR, because of the added 410 kVAR on the motor load end, the effective kVAR has come down to 418. Right, with the result, the power factor is increased to 0.89. So that's how we can increase the power factor in a circuit. If you see before and after, so this one is voltage and the light blue is current and the red is in waste and green is reduced waste. You will see before correction, the lag between voltage and current creates waste. Whereas after correction, the lag is very much less. Wasteful lag is reduced to increase the energy efficiency. This is the analogy how we do what we do it for power factor correction. Then understanding leading and lagging power factor. Leading power factor is when the current in the AC circuit is leading the voltage in waveform, as we have just seen. The power factor is called the leading power factor. Whereas when the current in an AC circuit is lagging the voltage in waveform, the power factor is called the lagging power factor. The leading power factor is caused when the net load is capacitive in nature, whereas the lagging power factor is caused when the net load is inductive in nature. Now, the inductive and capacitive loads cancel each other while responding to an electrical load supply. Since a majority of the loads by nature are inductive, the best way to improve the power factor is to add capacitors. The obvious advantages of improving the power factor are the reduction in distribution losses and improvement in voltage. That's the advantage of improving the power factor. And finally, difference between unity, lagging, and leading power factor, we are seeing voltage, current, induced inductive load waveforms, where lagging power factor, where current is lagging the voltage. Whereas in a capacitive load waveform, the current is leading the voltage. That's the difference. So that's the importance of power factor in an electrical load. It plays a very important role because most of the electrical equipment connected load in industry happen to be inductive in nature. So understanding the power factor gives a very much use to the energy conservation mindset of the employees. Thank you very much.